Let us take a look at linear programming with ellipsoidal uncertainty. So we are again looking at a linear program which is of the form C transpose X subject to A transpose X less than equal to B. So let's say that there is only a single constraint, but we are saying that this A vector is uncertain, and in particular we want to say that A belongs to an ellipsoid with center A0 and matrix P. Or in other words, we are saying that A belongs to this set. So A is some vector in Rn such that A minus A0 transpose P inverse A minus A0 is less than equal to 1. Remember that this is the specification for an ellipsoid. Assume that P is positive definite. Now this kind of uncertainty in A is different from what we have seen so far. We have only seen discrete possibilities for A. Now in this case, it is not the case that there are discrete possibilities. In fact, if you imagine A as a point in n-dimensional space, there is an entire ellipsoid surrounding A, or this is the point, you can say that this point is A0, and there is an entire ellipsoid surrounding A0 where A could be. So A could be any point in this entire ellipsoid, and we are allowing A to be any such point, and we want to solve this minimization problem, this linear programming problem, while allowing A to be any point in this ellipsoid. Note that we cannot use our earlier trick of substituting A with every single point, because this kind of specification amounts to infinite number of constraints. So this kind of specification amounts to infinite number of constraints, because in this ellipsoid there are infinite number of points, and therefore if you directly write it, it would not even be a problem that you can write down, because there are infinite number of constraints, and you cannot obviously plug it into a software, because in a software you need finite number of constraints. So how do we simplify this problem? How do we express it in such a way that the number of constraints is manageable and we can actually solve it? To get some intuition into this problem, let us consider the simpler case of n is equal to 1. So let's say that n is equal to 1, which means that x is a scalar, and we have a constraint of the form ax less than equal to b, where ax and b are all scalars. So in the n equal to 1 case, ellipsoid is essentially what? It is simply an interval. So let's say that a is between -1 and 1. So what does it mean for us to try to satisfy this constraint for all a between -1 and 1? We can write this constraint as max over a belonging to -1 to 1 ax less than equal to b. So in other words, we are saying that the value of a that maximizes the left hand side is basically the worst possible value of a for us, because for that value of a the constraint could get violated, and therefore we are ensuring that the maximum of ax for all a in this range should be less than equal to b. If the maximum is less than equal to b, any a in the range times x would also be less than equal to b. So when we say that a belongs to a particular range or a belongs to a particular set, all we mean is that the maximum value of ax over that set is less than equal to b. Now this problem can actually be solved in closed form. So what is the solution of this problem? Let's consider this. Let's consider this problem with respect to a. This is a maximization problem with respect to a. So what is the solution of this problem? So let us say that the optimal value is attained by a star. You can see that a star is equal to, you can take it as 1 if x is positive, because if x is positive it is maximized at a star equal to 1, and -1 if x is negative. So if I plug in this value, this maximum will be equal to, x when x is positive, and minus x if x is negative. or in other words, absolute value of x. So this thing, this maximization over a from -1 to 1 is essentially equal to absolute value of x. So this entire constraint can therefore be written as absolute value of x less than equal to b. In other words, our problem minimize cx subject to ax less than equal to b, where a belongs to this set -1 to 1, is essentially equivalent, right? It is equivalent to minimize cx subject to absolute value of x less than equal to b. This transformation is possible because we are able to recognize that whenever we specify a as belonging to a particular set, all we need is to specify that the maximum value of ax for a in that set should be less than equal to b, and then we can solve that subproblem. This subproblem that we had here can be solved, and it can be solved, and then we can get this result as absolute value of x. So let's apply the same idea to the original ellipsoidal uncertainty problem. So let's say that we have minimize C transpose X subject to A transpose X less than equal to B, where A belongs to this ellipsoid centered at A0 and matrix P. Now, as we have seen, we can write this problem as minimize C transpose X maximum over A in this ellipsoid A0 comma P and A transpose X. So this maximization is with respect to A, where X is a constant, is less than equal to B. So let me just emphasize this fact. This maximization is with respect to A while keeping X as constant, and the outer minimization is with respect to X. So now it remains for us to solve this problem. So let's write it down. It remains to solve this problem A transpose X with respect to A, where A minus A0 transpose P inverse A minus A0. This is the definition of the ellipsoid, is less than equal to 1. Right? So we need to solve this problem, and whatever solution we get, note that this will be solved with respect to A, and therefore this will yield some function of X. So whatever solution we get, we will substitute it here, and we will have our final inequality of the form gx less than equal to b. So that is what our goal is. So let's solve this problem. What kind of problem is this? This is a problem with linear constraint, linear objective, and quadratic constraint. So you can think of it as a QCQP. Now to solve it in closed form, what we can do is we can use the alternative definition of the ellipsoid. So when we say that A belongs to this ellipsoid A0 comma P, we can write this ellipsoid, if you remember, as A0 plus square root P times U subject to norm of U less than equal to 1. So this was the alternative characterization of an ellipsoid, where square root P is the matrix square root. You can verify that A0 plus square root P times U does indeed satisfy this constraint. So let's substitute this quantity, this A0 plus square root P U, in the optimization problem. So what we obtain is that maximum, so instead of A, we are maximizing over U subject to norm of U less than equal to 1. And our goal is to maximize A0 plus square root P U transpose X. So instead of A, I have substituted A0 plus square root P times U. And now the maximization problem is with respect to U. This can be written as, so this can be written as A0 transpose X plus maximum over norm of U less than equal to 1 U transpose square root P times X. So now we have basically taken out the constant because the maximization does not depend on X. Maximization is with respect to U. So the objective now is to maximize U transpose square root Px subject to norm of u less than equal to 1. So what is the solution of this problem? So let us look at it as an aside. So let's say for a moment that this is w. So w is square root p times x, and we are interested in solving the problem w transpose u subject to norm of u less than equal to 1. So how do we solve this problem? We can use a similar idea as earlier to maximize this w transpose u. Earlier we were saying that in a times x, it was maximized whenever a star was 1 whenever x was positive. So basically a star was in the direction of x. So in the same way, we can assume here that u is equal to alpha times w. Then the problem can be written as maximum over alpha times w transpose w, subject to the constraint that norm of w, alpha times norm of w is less than equal to 1. It is easy to see that the solution of this is given by alpha equal to 1 divided by norm of w. Right? So you can verify that. If I pick alpha equal to 1 divided by norm of w, then I will get the objective function will become norm of w, and the constraint will also be satisfied. So therefore, plugging it back, we get that u is equal to w divided by norm of w. Now you can verify, we started with this assumption that u is in this form. You can actually now go back and verify whether this value, so if I substitute this u star in the original problem, the value will be given by w transpose w divided by norm of w. So the optimal value will be given by this quantity, which is equal to norm of w. So we are saying that if we pick u is equal to alpha times w, then the maximum value this can take is norm of w. But note that in general, w transpose u by Cauchy-Schwarz inequality is less than equal to norm of u times norm of w. And norm of u is already less than equal to 1. So this is less than equal to norm of w. So in general, w transpose u is less than equal to norm of w. And we are saying that if we pick u of this form, then we already are getting norm of w as the objective function, the maximum value of the objective function. So therefore, this must be the optimum. So these two combined imply that u star is equal to w divided by norm of w is the optimum. Because at this point, we are getting the maximum value that the objective can take from the Cauchy-Schwarz inequality. So in this kind of proof, there are sort of two steps you can observe. In the first step, we assumed some form. We found the maximum if that form was true. And then we are showing that that maximum that we have found is anyway the upper bound on the objective function. So coming back to our original problem, we have now found that the maximum value of this is, so the maximum value of this is the norm of w. Substituting it, we obtain that, so this implies that our original problem becomes minimize C transpose x subject to A naught transpose x plus norm of w. W was square root p times x. So norm of square root p times x less than equal to b. So this is our original problem, and you can appreciate that this is indeed a SOCP. To see that it is an SOCP, you can write it as minimize C transpose x subject to norm of square root p times x less than equal to b minus A naught transpose x. So you can see that this is indeed an SOCP. So this was a robust linear programming problem formulation where A is having ellipsoidal constraints.